Okay, we would like, before moving forward, to go over some of the review questions. So let's try to solve some of these together with a little bit more explanation. So for instance, it asked you here for the following maps assembly instruction, what is the corresponding C statement? F, G, H, I are basically assigned to register S0, S1, S2, and S3 respectively. And we are giving you the assembly code here, and we are asking for a higher level language C statement. For instance, if you don't know C language for whatever reason, then please you can answer in the any of the assignments in any other language that you are aware of. This can be either Java, Python, any software higher level language that you are aware of. So we will be flexible in that regard. Let's go over these things together. So I'm telling you here that add G plus H, put the results in F, and then add F plus I, put the results in F. This does mean that you just can write this in one line code that F is equal to G plus H plus I. Of course, this is like as simple as that. However, in the quiz or any assignments, I actually write it a little bit differently, meaning that we will say like add, and then since we have S0 in F, so basically we will write S0. Since we have S1 in G, so basically this will be S1, and this is will be S2 for instance. And here you will have the addition again of S0 since this is F, and then the I will be S3, and then the F will be S0. So we might write it that way. Here it asks like for the following C statement, what is the corresponding MIPS assembly code? Please assume that the variable I, G are assigned to register S3 and S4. Assume that the base address of the arrays A, B are integer S6 and S7 respectively. So I'm giving you where is I and J, which is in S3 and S4. And I'm giving you also the base address of array A. Base address of array A is in S6. And we are giving you that the base address of B is in register S7. Base address means like the first element in that particular array. If I'm telling you that I'm giving the base address of A, which is in S6, meaning that A of 0, as an example, is in S6 if not otherwise specified. If I didn't specify anything or what is the exact base element number, I would assume that this is A of 0 or the first element. And basically that address is held or is written in register S6. Where is register S6? You will open the table and see where is S6, the number corresponding to S6, and then you will go to that particular address number inside the register, open that drawer, and then read the number there. This will be the address of the first array of A0. So basically, if we think of this, you might have the register like that. And here is my memory. S6, let's assume that S6 is here. As an example. And let's assume that S7 is here as an example. And I have like also other slots inside my registers. We mentioned that this is the register. It has 32 slots or 32 drawers. In S6 here, we actually have the base address of A of 0, meaning here address of A of 0. In S7, I have the address of B of 0, meaning that whatever is written in this slot is pointing out to a certain address here inside my memory. And basically, in that sense, it is pointing to address A of 0. That means basically that in this particular slot, I have actually array of 0, the value of array of 0. This is not but the address. This is what is exactly in A of 0, what is exactly in the first element of 0. I have also another slot here that is pointing out, for instance, to B of 0. Here is just basically the address of B of 0. From here, if you look closely at here, what I would like to do is I need to get A of I minus j and basically put the result that I have it in A of I minus j in B of 8. Meaning that if A of I minus j is here and B of 8 is here, if this is the case, I would like to take the result that is here, copy to this location. This is what I would like. As you know, in MIPS instruction or in RISC processor, this is not allowed. We can't do any operation directly in the memory. In order to do an operation like that, I have to retrieve back all of the information to the register, do whatever I would like, and then return it back to the memory. This is what we have agreed on. We are not allowed to do any job outside our firm. We have to bring everyone inside the firm, do the operation, and then return back the results to the customer. That gives me an indication that first, I need to know where is A of I minus j, then copy A of minus j in one of the slots inside the register, and after I have it, I need to copy it back to a location B of 8, but I have to know, of course, where is B of 0, and accordingly, I will know where is B of 8. This is basically the idea, correct? So the first thing we need to do is basically do or understand where is the location of A of I minus j. So the first thing to do is to do this subtraction, A I minus j. Where is I? It is in S3. Where is j? It is in S4. So the first thing I have to do is subtract S3 minus S4, and I can put the results in a temporary register. I will refer to that as T0. Okay, so now after I do this, then I have, like as an example, one of the registers here, T of 0, which have S3 minus S4, which is not but I minus j. So I know now what that number is. Because I went to drawer S3, I went to drawer S4, I read whatever the numbers which were there, subtract them, I have another number. I save that number in a register called T0. So now I know what is that number, or the computer already knew what is that number. But independent of that number, I have to follow these steps. After I knew that that number is x, as an example. So I know now that this is a of x, of any certain number, as x is equal I minus j. So now I know a of x. What else I need to do? If you recall from the example that we mentioned earlier for the houses, for instance, if we have a house here and then another house here and then another house and so on and so forth, if this base address begins with 800 and then I'm incrementing by 4, so this means that this is 204, this is 208, this is 212, 216, and so on, as this I is equal to 0, this is equal to 1, 2, 3, 4, and so on and so forth. In order to have a general formula, this means that we have the base address plus 4 multiplied by I. If you give me this, any of these, then I can give you all or any of the numbers. If you would like to know what is the address of I of 2, base address is 200 plus 4 multiplied by 2 is 8. 200 plus 8, it's basically 208. That means that I have always to multiply 4 by I because I am incrementing by 4, correct? My I here is basically x. Correct? So in order to know that address, I have to multiply the x by 4 as exactly I have done here. I multiplied the I by 4 because this is, I can write that this is house of 0, house of 1, house of 2, and so on and so forth. Here I have A of 0, A of 1, A of 2, and so on and so forth. So first I have to multiply it by 4 and then add that to the base address, correct? This is what exactly I will do now. First, I have to multiply this x by 4. And then after I multiply it by 4, I have to add this results to my base address S6, as S6 is the base address of A of 0. How I multiplied by 4? We mentioned also earlier that if I shift left by 2, that means that I multiply that number by 4. I can save it in T0, or I can save it in T1, or I can save it in any other register. Here, I have to choose to overwrite S of 0 with that particular new number. I'm just following the exact formula that I have used here. Base address plus 4i. This is 4i, or 4x. Then after I have this 4x, I have to add it with the base address, which is here. And then I'll put the results, let's say, in T1. So now I have, let's say, T1. And this is basically holding the address of A of I minus j. Now I know where is exactly the address of A of I minus j after I have done these things. I minus j is basically x, and then I multiplied by 4, and then plus the base address. So I know where is A of I minus j, or where is A of x, as x will be at the very end a number. So that means that basically as soon as I have this, I know that this is basically pointing out to a certain address here, which is address of A of I minus j. So this is basically the results of the correct of I minus j. What we have mentioned, or what we have, or what we can see from this, that actually I need to take that value and then copy it to my register, and then return it back to B of 8. This is what I would like. In order to take these data to my register, what I should do? We mentioned earlier that in order to talk to the memory, I have only two commands. Either read from the memory or retrieve data from the memory by load word, or writing to the memory by store word. Since I would like to go as a reading from the memory, so I will need to use load word. So I would load word that particular value, which I already knew its address, which is already saved in T of 1. That's why here I have load word, please, the data that is the address that is already held in T of 1. There is no shift at all because it is exactly that address. It is not shifted. It is 0. It means that particular address. Please copy that to T2. So what I have done, that I have taken basically this value, and I have copied here to T of 2. So basically here is not the address of A of I minus j, it is A of I minus j itself. What is that array element is basically holding? What is the value that is there? This value is in T2 according to this equation. Next, what I need to do? What I need to do, as we mentioned, as soon as I have the A of I minus j here, I have to copy this in B of 8. How I will know the address of B of 8? How I would detect the address of B of 8? That should be too easy because I'm giving you the first house and I'm asking you what is house of 8. House of 8 is not but the base address plus 4 multiplied by that number. Multiply plus 4i is exactly the equation that we mentioned. How to do that? What I need now to take this into here. So I need to use store word, that guy, which is in T2. That guy is in T2. Please go and copy this in B, array B of 0 address, but shifted by 32. So I will go to that. I know this is the address of B of 0, shifted by 32. Why 32? Because it is shifted by 4 multiplied by 8. Because we mentioned that it will do the base address plus 4i or 4x. And basically, we already knew that this x is 8. We are counting by 4. So please store the word or store of A of I minus j to that particular location. And now I am satisfying basically this code. So here it gives you, assume that register S0 and S1 hold the values this and this. What is the value of T0 for the following assembly code? Just add this plus this, put the results in here. And then is the results in T0 basically is a desired results or it has any overflow? So you can do this by yourself, but I will just like give you the hint or what or how you should think on that. It's basically, if you would like to do the addition, you would like to add this plus this actually. So you will do this 0x and d all zeros, and then 0x and 8 all zeros, and then you need actually to do that. When you do these additions, zeros, 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 and so on, d plus 8, you might get that as 15. But the problem that you are facing here, that basically if you count this, you will find that this is actually written in 32 bits, which is the same here. But now the results need 33 bits. But this is a problem because the maximum that you can save inside your register is 32, correct? So what you will do is what? Is basically saving this data only. So it will be 5, 0, all of these zeros as a hex. And unfortunately, you will miss that one, which is already actually should be included inside your results. This gives you an indication that the result that you have here, unfortunately, is not the desired result. And definitely overflow occurred. Overflow means that the number that I have to save is basically bigger than my space. Here, also asked you about the provide the type of hexadecimal representation of the following instruction. Store word T1, 32, and then T2. So I won't go over these in details, but I'll just explain how you should solve something like that. First of all, you need to understand what is the type, which is basically I type. Because we mentioned earlier that store word, load word, add I, and I, all of these kind of things are basically I types. If, for instance, you forgot, or if I give you another instruction that we did cover, how you would expect if this is an I type or this is an R type. So basically, if you will find that we need to deal with any constant, independent of what that constant is, constant either like referring to an address or an offset or any certain constant that I would like to add, then directly you have to expect that this is an I type. Because unfortunately, we can't write any constant as we explained in an R type. We can't do that. So we now knew that this is an I type. If it is an R type, you have to remember how the I type is constructed. We already explained that in an I type, I have here my opcode, I have here my RS, I have here my RT, I have here my constant. This is 6 bits, this is 5 bits, 5 bits, and then 16 bits. We also mentioned that independent of the instruction here, if it is load word or store word, I have to always deal with whatever inside this bracket as RS and whatever here is RT. Either load word or store word, and please do not forget that. So that means that this is T2 will be basically allocated in RS. This T1 will be allocated in RT. That constant 32 will be allocated here. Store word will be allocated here. How to refer each of these to its number? You will open the table that I have already shown you earlier. You will see what is the number that is corresponding to store word in that particular table. You will see what is the number or the drawer number inside my register or the slot number inside register that's belong to T1. And then you will simply include it here. You will do the same with the T2. And then you will simply put the 32 here in 16 bits. Concatenate all of these numbers and then put them in one number as a binary. If I asked you, show me this in hex, then you actually need to transfer this in hex, which you will find it like that. As I told you earlier, I may give you this and ask you this to get this, or the other way around. Here, it says that, okay, translate the following MIPS code to C. Again, you can write this in C, Java, Python, whatever the high-level language that you are aware of. Assume that the variable f, g, h, I, j are assigned in S0, S1, S2, S3, and S4 respectively. So this guy is in S0, in S1, S2, S3, and then S4. Also assume that the base address of array A and B are in S6 and S7. So this is for A, B, meaning A of 0 and then B of 0. What you need to do, of course, to follow all of these things to understand what is exactly the function that we are trying to implement. Let's try to go over these kind of things step by step. Remember that this is Sx hold the base address of A of 0, S7 hold the base address of B of 0. The first thing that we are doing here is add I, S6 plus 4, put that in T0. So if we were to have a register, S6 hold the base address of A of 0, I will add 4 to that and put this in T0. So if this is T0, for instance, this is the base address of A of 0 plus 4. If it is the base address of A of 0 plus 4, what I should conclude? So if I'm giving you that the first address in that street of the houses is basically 200. And then I have added 200 plus 4. Does that give you any information? While you already knew in advance that in that street we are counting by 4. So the first is 200. If I add 4, so this means that I'm giving you the address of what? The next house, correct? So that means if I have the A of 0 and I add 4, so that means that I'm giving you the address of A of 1. So I should be smart and understand that this is not but the address of A of 1. The next thing here, that add T1 SX0. So I'm adding the base address of A of 0 to 0, put that in T1. So I did nothing. So basically now in T1 is address of A of 0. But here is address of A of 1. So now in T0, I am holding the address of the second house. In T1, I hold the address of the first house. Or by another meaning, in T1, I'm holding the address of A of 0. In T0, I'm holding the address of A of 1. What I am doing next, that, okay, if this is the case and I have here my memory, I am doing interesting things here with this instruction. Store word T1, comma 0 T0. What does it mean? Store word, whatever is in here, to that particular place inside the memory. First, I need to know what is this. T1 is address of A of 0. Where I should copy that? I should copy that to the address of T of 0 is not shifted by anything. So it is exactly the address of A of 1. So what I am doing here is not but writing that address into whatever I am pointing out as address A of 0, as address A of 1. So that means that this guy T of 0 is pointing out to a certain address. Let's say pointing out to that address. as this is A of 1. This is address of A of 1. And this is A of 1. And this T1 is pointing actually to address A of 0, which here I have A of 0. This is pointing out to that particular place. What I'm doing is store word T1 to that particular place. So where is T of 0? T of 0 is pointing out to this one. What is T1 is basically pointing out to that one. So what I am doing is I'm overwriting A1 with A of 0. Because whatever is there was A of 0. T1 is holding the address of A of 0. So what I am doing here is basically storing whatever I have in T1 is in whatever I have in T0. So that means that whatever I have here should be basically right whatever I have inside my memory. After that, I have to take that particular thing that I have already wrote that. So this is address of A of 0, whatever I have here. And I have to take it back to T of 0. So overwrite here. So now the overwritten is telling me that I have overwrite this by address of A of 0. Remember that whatever I had here is not A of 0 by itself, it is the address of A of 0, because this is what I have already stored from T1. T1 is hold to the address of A of 0, so the address of A of 0 is here. Now load word that, so it is address of A of 0. Then add T1 with T0, put the results in S0. Add both of these, put the results in another place called S0. So S0 is not but 20 plus 21. What is in T0? Address of A of 0. What is in T1? Address of A of 0. So that means that actually I am getting the address of A of 0 plus the address of A of 0. All of these is in basically S node. So in S node, I have to multiply it by the address of A of 0 in S node. What is S node? S node is F. So F equal 2 multiply the address of A of 0. So 2 multiplied the address of basically A. Another question here is asking you, please, I will not go over this in details, but I will just explain the concept. Find a sequence of MIPS instruction that extracts basically from bit 16 all the way down to 11 from register T0 and uses the value of this field to replace bits 31 to 26 in register T1. So basically, you have here a register T0 from 0 all the way to 31st. I am telling you that from 11 all the way till 16 is basically here. I have also another register T1 that is basically again 32 bits. And I would like these values, for instance, here to basically replace from 26 all the way till 31. So basically, I would like that this will overwrite whatever is here. And nothing here will change. So this will stay as it is. Here we are showing a code that is representing these things. You need to go over it step by step and then follow it, and you will understand that we are doing this. Exactly what we have explained here. But does that mean that this is the only option? The answer is no. There are many options that you can actually try by yourself. In fact, there is another option that you might do this in maybe 3 or 4 lines only instead of all of these lines. There is another option that you can do that. So please try to think by yourself and try to do all of these kind of tricks by yourself. In this question, we are just asking that please write the C statements, which is the maps from the maps assembly instruction that does this identical operation. Assume that T1 is equal to A, T2 is equal to B, S1 is the base address of C, and A is equal to C0 shift left by 4. So basically, the first thing, of course, to get C of 0, you already knew that S1 is basically the base address of C. So you already knew that this is here. You will take that to your certain registers, let's say T3 inside your register. So you have here basically T3, which is holding whatever inside the address that is pointing out by S1. So you took these things, which is C of 0. You copy it here. And then after that, you have this value in T3. You have this value in T3. So you have here C of 0. What I need to do is just shift left by 4. So shift left by 4, T3 shifted by 4, put the results in T1. Here it says like assume T0 is holding this value, basically. What is the value of T2 after the following instruction? So here it says like SLT set less than. So you are just checking to see if basically 0 register is less than whatever I have in T0 or not. If you remember with the set less than, that basically in this case, if it is true, T2 is equal to 1, else, so this is if true, T2 is equal to 1, else T2 is equal to 0. We have already explained what the SLT means, set less than. So if this is true, if 0 register is less than whatever the value that is in T0, if this is true, I would expect that this is equal to 1. Of course, a lot of tricks we can play with these numbers, correct? Because we can write this in 2's complement, and you need to know if this is less than or not. And then I'm asking you BNE, branch not equal, means that you will check if T2, which is now 1, is not equal to 0 or not. Branch if not equal. Actually, this is equal to 1, assuming that this is equal to 1. So they are not equal. So you will go to else. What is an else? Else is not but add T2, which is 1, to 2. Put the results in T2. So we'll put 3. So what is expected in T2 is just 3 in this case. But assuming that if actually is not, this was 0. So if this is 0, when you check this is not equal or not, you will find no, this is not true. So you will not go to else, you will just jump to done. So that means you will jump here to done. What is in T2? What is in T2 is basically whatever you have here from the very beginning, which is 0. This is actually the other route, if it wasn't true. Here, write a MIPS assembly code that create a 32-bit constant, and this is the you have, and store that value for register T1 So actually, you can still do that. One thing that I would like to highlight right now is basically this code is LUI. Load upper immediate. What does that mean? We mentioned load word, correct, earlier. What is load upper immediate? Load upper immediate that I am loading the most significant 16 bits into T1. So load upper immediate T1. So that means that I am basically loading the most or the top 16 bits. So there are like basically different ways to write that, but at the very end, it will be something like that. So I am now expecting that you are aware with what is LUI.